The set of positive integers is partitioned into n disjoint infinite arithmetic progressions S1, S2 up to Sn with common differences d1, d2 up to dn respectively. Prove that there exists exactly one index 1 is less than or equal to I is less than or equal to n, such that 1 over di times the product of all the common differences is in the sequence Si. So we're going to actually take it a step farther and prove that all of these terms are actually the same arithmetic progression. And we're going to do that by first proving a few lemmas. First of all, we have lemma 1, which is that for all sequences, for all Si, the first term of the sequence, the first term is at most di. So the first term is at most the common difference. It can't be any bigger. And the way we're going to prove that is using contradiction. Proof by contradiction. We're going to assume that, let's say there's an arithmetic progression without loss of generality S1, such that the first term is greater than d1. So in S1, assume the first term is greater than d1. So we can write it as a plus d1 for some a is greater than 0, right? So a plus d1 is in S1. But a is not in S1. Otherwise, a is the first term instead of a plus d1, since a is smaller than a plus d1. Okay? So we're going to assume that a is in some other sequence. And without loss of generality, we're going to assume that the sequence is S2. It could be any sequence, really, but S2. Right? So S1 consists of a plus d1, a plus d2, a plus d3. No, excuse me. It is a plus 2d1, a plus 3d1, right? This makes more sense because each time you're adding d1 to get the next term of the sequence. And S2 consists of a plus d2. There might be some terms before this a, but really we're only paying attention to anything that's a and beyond. A plus d2, a plus 2d2, etc. Right? Okay. Now consider this term a plus d1, d2. I'm going to claim that this term has to be in both sequences, and it's in sequence S1 because it's a plus a positive multiple of d1. It's in S2 because it's a plus a positive multiple of d2, right? Their common differences can't be 0, otherwise you can't divide by 0 over here. So a plus d1, d2 has to be in both S1 and S2. But remember, we're given that the set of positive integers is partitioned into n disjoint arithmetic progressions, which means that each positive integer goes into exactly one arithmetic progression. So therefore, this term over here cannot be in both of these. And this is a contradiction because we proved that it is in both of these. So that's enough to prove this lemma, which is that for all sequences, the first term is less than or equal to the common ratio. And that's pretty small, but it turns out to be actually pretty useful. Okay. Now let's look at another lemma 2, which is going to be that the sum of the di's, 1 plus d1 plus 1 plus d1 over d2, 1 over d1 plus 1 over d2 plus 1 over d3 plus etc. plus 1 over dn is equal to 1. And the way we prove this is we take the least common multiple of all the di's. We're going to call this a, some number a, right? And let's take a look at the positive integers 1, 2, etc., all the way up to a. Each of these is going to be in one of the sequences, right? However, exactly a over d1 of them are going to be in sequence 1. So d1 of them are in sequence 1. And a over d1 has to be an integer because a is the least common multiple of d1 and some other stuff, right? So a over d1 of them are an S1 because, well, think about it. If exactly one number from 1 to all the way up to d1 is in A. Exactly one number from d1 plus 1, d1 plus 2, etc. to d1, exactly one number from this range is in the first sequence. And this is because of lemma 1. For all si, the first term is at most di. So the first term has to be in this one, then you add di. The second term has to be in this range, and so on. So a over d1 of them are in S1, a over d2 of them are in S2, etc., right? So total number of the terms that are in any of the sequences is a over d1 plus a over d2, a over d2 plus a over d3 plus etc. plus a over dn, right? This is the amount of terms in each of the n sequences, right? However, since each of these has to be in exactly one sequence because it's a partition, this is equal to a, and we can divide both sides by a to get our desired sum of these fractions. So that's enough to prove the second lemma. Okay. Now, what am I going to do? But I'm going to prove a third lemma, which is that, okay, let me write this down, lemma 3. Um, 1 over di times the product of all of the d values, j equals 1 up to n of dj, is still divisible by d1 di. Okay, and let's go ahead and prove this for d1, and then we can generalize what we did to nei. Okay, so we're going to start by showing that this statement is true. 1 over d1 times the big product is divisible by d1. Then we'll do it for nei. Okay, and what we do is we take this expression and we say, okay, 1 over d1 plus these other fractions we can write over a common denominator. So it's going to be stuff over d2, d3, d4, dn, right? You can write all of these over a common denominator, d2, d3, d4, dn. And this stuff is going to be a positive integer. This is going to be equal to 1, right? So we can multiply both sides by this d2, d3, d4, etc. dn. You get d2, d3, d4, dn over d1 is equal to d2, d3, d4, dn minus the stuff that we had on the numerator, right? However, this product is a positive integer because all of the di's are common differences, which are integers, and the stuff is a positive integer because, right? Because since we wrote this over a common denominator, the stuff is a positive integer, which means that this thing also has to be a positive integer. And the only way that this can be a positive integer is if this stuff is divisible by d1. However, we can rewrite this as 1 over d1 times the product of all of the differences. This is going to be 1 over d1 times the product of all the differences. This is going to be 1 over d1 times. We can write this in product notation as this thing we had over here, right? Which means that this thing is on the numerator and d1's on the denominator, and this divided by that is a positive integer. And what that means is that this thing over here is divisible by d1. And we can do this for any I, not just one. We can generalize this, and that is enough to prove our lemma 3. Okay? So now let's go down to the actual proving. Okay? So let's look at I equals 1. So this 1 over d1 times the product of all the di's. J equals 1n dj, right? And we know this is equal to d2, d3, d4, dn, because this whole product is just the product of all the differences, and this should be the product of all the differences except for D1. So this is a multiple of D2, D3, D4, etc., Dn, right? That's obvious because it's D2 times some positive integer, D3 times some positive integer, right? It's also a multiple of D1 by lemma 3, right? Now let's say that this term, which we'll call x, is in a sequence SA, some sequence A, right? So this x is equal to dA times something, let's say some constant, right? X is equal to dA times some constant. However, lemma 1 states that for all SI, the first term is at most di, which means that the first term is at most dA. But since the common difference of this sequence is dA, not only is x in the sequence, but dA times c minus 1 is in the sequence. dA times c minus 2 is in the sequence, etc. And then eventually you can conclude that dA times 1 is in the sequence, right? Because if x is dA times some constant c, and the common difference is dA, then really the sequence just contains all multiples of dA, which means that the first term is going to be just this dA over here, right? So all multiples of dA will be in SA. So you can write SA is all multiples of dA. However, we proved that for any I, this thing is a multiple of dA because it's just, well, first of all, by lemma 3, when I is equal to A, you have that 1 over dA times the product is divisible by dA. Otherwise, this product is equal to all the product of the differences except for 1, which is not dA, which means that the product, this thing over here, includes dA, like it's D1, D2, something, something, Dn, but excluding one index, which means that this thing would be divisible by A. Anyhow, so all of these terms are actually in SA. So every single term is in SA, which means that the only index such that this thing over here is in this thing, the only I for which this works is A and nothing else, because SA contains all of them. So none of the other sequences contain any of them. So that is enough to prove that this statement holds. So we are effectively done. Thanks for watching, and I will see you next time.